Okay. So what we had discussed yesterday, it was about how we have the um, second order model of say SMIB system, and we had the some of the equations derived, and then having an understanding how does the natural frequency or the damping ratio or the damp frequency will change as the system parameter changes. So here we had the synchronizing torque coefficient, damping torque coefficient, and the inertia. So how do these parameters, because you see, these are the system parameters, because once you have your generator connected to the line to the infinite bus, okay, that is constant. Then same way the damping torque coefficient, because once you have your load and the load is fixed, so it is constant. Same way the inertia, once you have your generators and then again all the systems intact, so everything in position, so it is constant unless you add some more generators or you add some lines or you trip some lines. All right. So unless you do some changes in the system, these parameters will remain constant, and thus the variables. These are actually the system parameters. This you can say the system parameters, and this one you can say the operational quantities, because the natural frequency, the damping ratio, the damp frequency, all these can vary, right? It will change. So these are the, you can say, the operational quantities, operational variables here. So next I have an example to discuss uh, the modeling part and then again the analysis part. It is as a small signal analysis for SMIB system. And I have this example from the Kundur book 12.2. So they have several generators, in fact. So there are 4 number of generators of this much capacity connected through, this is the generator terminal, and through the transformer, and with the line, they are connected to infinite bus system here. So this is what it describes here, the complete SMIB system. And here they have said, okay, the resistance of the line to be neglected, that then the reactance of the 2 parallel lines are given here. What is the reactance of the transformer? And then power capacity of the entire power plant, you can say. Now, we want to analyze here a small signal stability characteristic here. All right, so it will be about a steady state condition, about a steady state operating point. So we say that it could be, let's say, loss of one of the line here. All right, so this line is stripped. So, and we say that the post-fault condition after the fault, all right, it is this way. So we have the power this much. This is in per unit, reactive power, and the voltage at the bus here, this one, and the voltage which you have it here. So you can see the reference angle at the infinite bus, it is 0 degree, but the voltage magnitude at the bus, infinite bus, it is something different here. And then but the voltage at the generator terminal, you consider as your one quantity, 1 per unit. Now, we have considered all the generators as equivalent generators here, and the reactance of the generator is given, and then what is the inertia here, right? So we will consider a linearized state equation of the system based on the previous discussion. We'll determine the eigenvalues, what is the damp frequency, damping ratio, and undamped frequency here. Now, as I said, the load damping constant. All right, so you have to solve this part. You have to solve this part based on the previous relationship, this one, right? This one saying that the load damping constant, because that means the term here, this one. This is zero. You can say the load damping constants is zero, or maybe somewhat negative, or it is positive here. So we'll find out how does these parameters, damping ratio and damp natural frequency, will change with these quantities here. Then for this case, particular case, find the left and the right eigenvectors and also determine the time domain response. So these are in the two parts. The first part refers to steady state analysis, and the second part is mainly understanding the time domain response here, right? And thus, as a solution for the first part, now we can have this is actually, you can say, the block diagram, yeah, right? Or in fact, sorry, this is, we say it as a single line diagram, yeah. So this is your single line diagram, and from the single line diagram you can represent them by a reactance diagram here. So this is the generator source you have represented here, right? So this is, we have written as E prime here. So this will refer to the induced EMF. All right, the value of electromagnetic force induced in the generator stator here, and with the angle delta. Now this quantity is the reactance here, direct axis reactance of the generator, and this bus here, this bus is this one here. And this is actually because transformer has two sides. So this is low voltage side, low terminal side, and you can say this is high terminal side, high voltage side terminal of the transformer, because you will step up the voltage through the transformer here. So, and then it is said that the voltage at the generator, in fact here, it is one quantity, one per unit. So it is this one. Then this, and since it is said the line is stripped, all right, one of the line, the circuit, this one, it is stripped. So the adjusting line, it is this one here. So what you have, it is this one here, right? And then you have it high tension side, and then in fact the voltage on the bus side here, to this one. So this reactance represents for the transformer, this reactance for one of the line here, right? Now we have to know, because at the moment you know the voltage, you know the voltage here, and you know the voltage here, but you do not know what is this voltage here, because the power transfer will take place from generator stator here, and again in between you have this reactance here. So we want to know what is the power flow from this point, basically, right? In fact, instead of saying the power flow right from here, we will say what is the power flow from this side, basically. So we will compute the current here, this one. So for that, what is it is given here, what is P and what is Q, right? So we write in this way, and the voltage, which is this one. So this is the value of current. Now this is the value of the current which will flow here from the generator, so right, and it will be across this reactance. So that's the voltage we should get it, the voltage behind the transient reactance. So this is the transient reactance, and the voltage which you get it here, it is this one here, right? And with that, what you find, this one. So this is so applying the Kirchhoff's voltage law, this quantity, and then product of this one. So you get it this one. So this is the magnitude of the voltage which you get it here, and the angle delta, it is this one here. So it means that the initial angle delta naught actually, right? That will be equal to, because here you at this bus the angle is 36 degree, but over here it is 13.92. So you sum it. So that means the angle in the generator rotor, it is 49.92 degree here. That is the initial. That means the voltage, this voltage leads the voltage here by angle of this much here. And then since we want the power flow, so you take the total reactance here. So this reactance, we have it from direct axle reactance of the generator. This is for transformer here, and this is for one of the line. It is this one. So you have it. So there is a total reactance. Then you compute what is synchronizing torque coefficient here from this relationship, which we had it here. In fact, this is what we had it here, right? And so it is E prime into EB. So this magnitude, just remember that this is magnitude quantity here. And then cos of delta naught, it is this one. And then the total reactance here. It is this. So the synchronizing torque coefficient, it is this much here. So with this calculation, then we can, if we refer from this one, we had this representation of the system as a state equation here. So from this relationship or representation of the state equation form, we had it this one. So we just substitute here the value. So again, we said the KD value could be 0 or something or any value. So we have just in general. So we substitute 2H and then synchronizing torque coefficient. We solve this part. This is 0 and then omega naught 377 here. And then we solve this part, we get it this way. Now, the eigenvalues of the state matrix, they are given by this one. Now, in fact, as you can see, because if you refer here, this is your characteristic equation here, right? So we had this characteristic equation representation from this A matrix here, this one, right? So because we have solved, because we have written down del delta from here, it is in this way, and out of this you have written, this is the characteristic equation form here, right? And then when you look at this is how we write the eigenvalues when you do it manually, right? So that means this is the A matrix here, the elements of the A matrix, all right? And then this will be corresponding to lambda 1 and this will be corresponding to lambda 2 here. So we have this in general quantity here. And we solve this, and then this is the form this way, the general form. And from here, you compute what is omega n. So we just compare this quantity with this one here. So with this, we write this one, and then solving this component with this one here. We solve it this way. So this is omega n, and this is zeta here. So eigenvalues, what you get, it is this way. This is the general, remember, this is the general relationship, what you write it for eigenvalues here. This one, minus zeta omega n plus minus omega n into under root of 1 minus zeta square. So this term, if you remember, it is actually the omega d. If you refer from previous, this one, it is this one quantity. Yeah, it is the same thing over here. This quantity. Yeah, it is written here, in fact. So now, since it is said in the first part to determine eigenvalues and then frequency, damping ratio, and then frequency for these quantities of KD. So with that, we have a table here, in fact, and With the table, you can see what are the eigenvalues. You substitute over here the value of KD. We substitute the value of KD here and then find out what is omega and zeta and then eigenvalues. So this is what they have done. For KD is equal to 0, KD is equal to 10, and KD is equal to minus 10 here, right? Now, what you find here, when the damping, the load damping constant, load damping constant is 0, the damping ratio is also 0 here, right? And when the load damping constant is positive, right, it is this much. And when it is negative, so it is this much. So you can see here that if there is no load damping constant, right, which will be basically form a frequency sensitive load, then in that case there you don't have any damping ratio. And of course you can see here how the eigenvalues are represented, where they will be located on the S plane. Yes, please. If you have the eigenvalue
on the left side.
yeah, but there is no real
this
part.
is 0.
Yeah, the real part is
This is
0.
going to be on the imaginary line.
Only on the imaginary axis. So it means that
yeah.
you will have their representation on the complex X plane that will be somewhere, let's say this one, and then again one is somewhere here. So this is 6.39 plus minus here, right? It will not, because this axis is your real part here, right? So you don't have anything here. But if you have 10, if you have load damping constant 10, then you find that the eigenvalues, so they are negative. So that means it has some real part here. It has some real part minus, and then it is, but you can see it is 6.39 and here it is 6.35. So that means the angular frequency has comparatively reduced, right? So I can say something here. Let's say, so the location of an eigenvalue, it is something here now for k is equal to 10. But if you have minus, if the load damping constant is minus, so where is the eigenvalue located? It will be on the
left side.
Right hand side.
Wait, minus isn't minus on the left?
Yeah, minus is in the left here. Minus is in the left. Yes.
Okay.
Yeah. Minus is in the left and the positive is in the right hand side, right? This is, if you know, this is, we call it as right hand side, right? Right hand side plane. And this is your left hand side plane. So left hand side plane means it will be actually minus real part here, minus real part, and this side it will be plus real part here, this side. So when you have positive eigenvalue, so they will be placed on the right hand side of the plane, right? Left hand side, remember, it is minus. Okay. Yeah. This is minus here, and this is plus. Okay. So if you have negated the load damping constant, so it means that the eigenvalues are located on the right hand side here. And if you have them on the right hand side, it means that, and again, what you see, the damping ratio, what is the sign here? It is minus. So it means that what will be the oscillation? What will be how the angle, rotor angle delta will change if they have a minus damping ratio? If you have a minus damping ratio, how it is expected to change? Let's say, what was the initial angle? Initial angle, when you look at it, was something 49.92, right? And if there is some disturbance, right? So then it will, because if it is a negative, then your response will go on oscillating and with increasing amplitude. So it will be somewhat increasing actually, right? So you will have increasing amplitude. So with damping ratio, negative means increasing amplitude of oscillation. You will also, right? So that's what you understand from this steady state analysis here. Okay. And the next part is the time domain uh, response analysis. So we write down right eigenvectors as this one, and and then they have said it for you. Do this time, get the time domain response for kd is equal to 10. Yeah. So we do this way. We had this. That means we have substituted the value of kd here. That is 10. So this is minus 1.43, and that's the same value here, which you have it here. In fact, it is this one from the characteristic part, equation part here, this way. So we get the eigenvalues as this one. And now what you find that there are terms here 511, 521, 511, and 521, and they are not linearly independent. And thus we have to get the eigenvectors here. So we will set it this quantity as one, and then is solved. In fact, in the MATLAB, I will show you, you can do it with the MATLAB, you can always solve it this way. All right, but you should know how to do it manually, basically. So because this is just for second order system. So if you have to do it manually, so this is the process here. Similarly, for the another eigenvalues, which you have it here, you substitute this one quantity as unity, and then you solve it 5 and 2 here, right? And then you get the right eigenvector. So this is the right eigenvector. Remember one thing, when you have the right eigenvector matrix, uh, when you go column wise, will be always representation for the eigenvalues here. And here we have two eigenvalues. This second one is this, and the first one you had it here, this one. And since it is a second order system, and you have two eigenvalues, this is lambda 1 and this is lambda 2 here. And what you find here that both
They are
eigenvalues,
complementary. No?
yeah, it is conjugate values. Yeah,
Conjugate, yeah, I mean.
conjugate value. Yeah, right. So if it is a second order system, and there will be always two eigenvalues, and then in this case it is a conjugate value, right. And so representation of the eigenvalues for the eigenvector, right eigenvector matrix, it will be column wise, it will be eigenvalues, and the row wise, it will be the state variable. Also, the way you had the state variable in the matrix, so omega and delta. So row wise, you go as a state variable, column wise, you go as an eigenvalue. And here you can see that if you have referred my the lecture on small signal stability analysis, so here you find that the angle delta, right, it is this one angle, because this is dial omega. So dial omega corresponding to eigenvalue this, and dial omega corresponding to eigenvalue this one, and del delta corresponding to this, and del delta corresponding to this. So that means the activity of state variable for a given mode. So what you find here is the activity of rotor angle is more, because this is unity value. However, if you take this as a amplitude, all right, you convert into polar quantity, so the amplitude, it will be much lower than unit quantity here. Thus the In fact, the right eigenvector tells you the activity of a state variable for a given mode here, right? So how the what is the activity of a state variable for a mode? All right, this is what we understand from the right vector matrix here. It is, and that could be uh, more useful to when you have to analyze the mode shape here, because right eigenvector, what you have it in this way, right? So it is the angle delta that has the maximum activity observed for for the eigenvalue here, right? Then there's one more point, we will compute the left eigenvector, but here it is shown in the solution getting it normalization. So the product of the left eigenvector and the right eigenvector, yeah, we put it equate to 0. So for that, so here what we have done is the normalization of the left eigenvectors here, and we use this relationship. And so from the previous part, you can see this one, the phi. So you take the inverse of this quantity. So that means the transpose. All right, so you have transpose the phi, right eigenvector matrix, and then you take the amplitude here. So you take the amplitude here, and then you compute what is the left eigenvector matrix in a normalized form. So you get this one. Then again, you find that again, when you talk about the left eigenvector, the column wise, it is the state variable representation, and the row wise, it is the eigenvalue representation. All right, so just opposite way. So for the left eigenvector, column wise, you go state vector, state variable, and the row wise, you go eigenvalue here. And with the left eigenvector, what you understand, it is this quantity, because when you refer to, because it is dial omega, which is the column wise here. So you find that it is the dial omega has higher magnitude, right? It has higher magnitude with respect to dial delta here, right? And for the each mode. So that means this quantity and this way. And if you go this quantity or this way. So that means the contribution of state variable omega to the given mode is more as comparable to delta here. But here we only understand by this what whether it is omega which contributes more or delta which contributes more. This is one part. We get it from left eigenvector. And then if you go to right eigenvector, we understand the activity of which state variable is more with respect to the other for a given mode, right? It is this one. So one right eigenvector, remember, we understand the activity of the state variable, and with the left eigenvector, we understand the contribution. But as a whole, it does not give you clear information. And for that, we want to compute the participation factor or the participation factor matrix here. And you can see here that it is nothing but the product of the element wise, the right eigenvector and left eigenvector here. So it is right eigenvector and left eigenvector element here. So it is the product of the element wise, the P matrix. And this is what we get it here. So now in this case, what we observe that for a uh, for the given mode, right? For the given mode, the the level of participation for both the variables, they are equal here. All right. So either you consider the omega or you consider delta, the values which you have it here, they are same here. right? So this is what we understand by participation factor. That means which state variable has the dominant representation of a mode, and we find that both the now in the when you do the participation factor, this white, this is the state variable. Remember, I have not indicated, but if you refer my video recording, so on this row wise, it is state variable, and column wise, it is eigenvalue. All right. So you find that here it is del omega, here it is del delta. So the level of participation either for omega, del omega, or del delta for the eigenmode this or the eigenmode this, it is same here. So that means uh, the uh, the uh, there is a oscillation, if there is a oscillation, then the equal amount of oscillation is observed, right? In both the state variables, omega and delta here. So that means both the state, that means the participation of the uh, these two state variables for a given mode, they are equal here. And next one refers to how to compute the time domain response here. So we have represented them in the form of a sum constant and exponential term here. It is this way. And we have this, let's say, this is what they have considered, let's say small angle delta. Because just see, in the first part, basically we had the steady state analysis here, right? But the second part refers to time domain. So if you want to analyze the system response in a time domain, you have to perturb it. That means around the initial steady state point, you have to consider this much change in the angle. What was the initial angle? It is this one. The initial angle is 49.92. And around this initial steady state point, you apply some delta change here. So it is this one, 5 per degree here. So this is in radian. And omega is this. So thus we get what is the value of C1 here. And this is value of C1 and C2. And then we can obtain what is the time domain response here. So we solve this relationship and get this way. Similarly, you can always obtain what is the rotor angle deviation this way, and we solve this one. Now, in fact, they have not given the response, but what you observe that this is a second order system, right? And thus there is a oscillatory mode because the eigenvalues which you have it here, they are complex eigenvalues, right? And they have a damped frequency of this much. So, and that means it is all the damped oscillating frequency, it is 1 hertz something. And the oscillation will decay, right? It will decay with this much time constant. And the damping ratio is this one. So, and again, in this case, rotor angle, both speed deviation and the rotor angle, they participate equally to this mode of oscillation here. So this is how we do the numerical calculations or numerical solving the system analysis here. But maybe I can show you how we do it in the MATLAB. So in the MATLAB, you have this matrix here, right? Because I had this matrix, this one. So this is the A matrix here. And with the values you substitute here, and then you can solve them. So in the MATLAB, they have, if you look, if you help EIG, this is the function which can be used to compute the eigenvalues and the left and the right eigenvectors here. So here you can see that EIG function, it computes the eigenvalues and the vectors here. If you use this syntax, so it will only give you eigenvalues here, okay? If in the left argument, you have only this syntax, so it will only give you a column vector, which will have an eigenvalue, set of eigenvalues here. for the square matrix. Here you have defined the matrix there, right? Now, if you use this form of the left argument in the syntax, yeah, then this will the D will give you a diagonal representation, diagonal matrix. It is a diagonal matrix with a representation of eigenvalues in a diagonal form. So that means the here you had a column representation of the eigenvalues, but now they are referred to diagonal representation of the eigenvalues here, right? And then next one, if you use this here, it is a full matrix omega, and you have the left eigenvectors. So you get the eigenvalues, you get the diagonal representation of the eigenvalues, and then again the uh, with the omega w, you get the left eigenvector here. That is possible. So you can use any of them, and then depending upon what you require, basically here, right? So in fact, I had solved it here. So it was this way. So I had this one PDW and then obtain this. But when you look at, but one thing, this is simple form. I have written it here because I have not normalized here the quantity. I have not normalized it here. And as such, when you go compare with this one, because you had the eigenvalues here, this one. So in fact, you find the eigenvalues minus 0.715 here something and 6.35 here something here. It's this, and thus there are two. I have solved it for KD is equal to 10 here, right? And this is what you get it. And then we want to look, when you look at, it is basically the right eigenvector here, right? So you can see this is minus the first row, and the second row, when look at, this is actually 0.00 I. So there is no imaginary term here. It is only unit value here, real part. It is this one. And then maybe if you take this part, so it is the same way you have represented here. It is this one. So this is your right eigenvector, right? Then, but in the solution here, they have done the normalization for the left eigenvector. So, but I have not done the normalization for the left eigenvector. So this is actually the left eigenvector, but I have not normalized it here. And this is the diagonal matrix, which represents the eigenvalues in the diagonal form. So you can see this one, because the eigenvalues are here, this one. But this here, with this syntax, they are represented as column vector. But with the use of D in the left argument in the syntax form, then they are represented as a diagonal representation. So that could be used to solve such problem, right? If you have anything on this, yes, please.
No, it's okay
Okay.
for me.
Then the next part, what we have, the further analysis, because we had considered the second order model of generator here, right? Because when you look at here, you had considered second order model. It is just simply as a inertia model of a generator or the turbine generator circuit system here set. But next we want to have the one more state variable, and we will take into account the generator field circuit here. And but again, generator has several field circuit windings. In fact, it has damper windings also, large generators basically, and that we call it as emeritus winding. But here we will not consider any effect of damper windings here, right? So we will neglect that part. We will consider only, so thus you may go into detail here in this section for the in the Kundur book. Then we can write the torque, electromagnetic torque, as this form here. So what you find it here, it is written down in terms of some constant K1 and K2 here. And K1 is related to del delta and K2 is related to field circuit here. Then the field circuit flux, this is the field circuit flux here, right? The incremental change in the field circuit flux here. So we write it in this way, right? And then in fact, the time constant, which we have it in the relationship, it is written down this way. So you don't need to go into the derivation of this relationship, but okay, if you can, if you are more interested, so you can refer this section here. And in fact, it is on this page here. They have discussed more in detail, but I'm not going to discuss that part. But because our intention is to understand the system behavior with the control part. So I state where I take into account the model with the control here. So thus, with the state variable from the field circuit part, now we have the third order model. So this is actually, now here you find there are three states here. The previous relationship what you had, there were two states here, right? But now with the field circuit inclusion in the generator part, we have one more state variable. That is basically the change in the MMF, change in the magnetic force along the direct axis in the field circuit here. It is this one. And these are the constant in the same way what you had it basically written down in terms of this system parameter here in this way. And then you have these state variables. And now just say the previous relationship has the input turbine power, or the mechanical torque from the turbine side. But now when you include the field circuit, it has additional input, that is the field voltage here. So this corresponds to the field voltage as a input to the generator rotor circuit here. This one. So now in this case, there are two input. All right. So one is the turbine power, another is the field voltage. I will show you later on in the block diagram. Yeah, here it is. So now if I go back to the previous block diagram representation, it was here, this one. So this was the block diagram representing the second order model. So you had Ks from del delta, you had only turbine power as an input here. And then you are understanding how does the rotor angle will change here based on the inertia and the load damping constant here, right? But when you include the field circuit, then the equations are modified. And with that, you can say, let's say, this part, what you had it from the previous block diagram, it is this one. Now, again, here, in fact, we have manipulated the previous block diagram and written down in this way, 1 by 2 HS plus KD. From the previous part, we can write down. And then here you have del delta, which is the integral of del omega here. Then one more part from the previous, here del TE, change in the torque here. That is K1 times del delta plus K2 times del psi, right? So this is del TE. This is the electromagnetic torque to the generator that is developed in the generator. This is the electromagnetic torque developed in the generator. And this is the turbine power or the turbine torque input here, right? And this del TE is K1 times del delta here from the previous relationship. K del T is the sum of K1 times del delta plus K2 times del psi D. So this one. So, and then you can say K2 times del psi D. So del TE is K1 times del delta plus K2 times del psi D. So it is del TE. Then del psi FD here. Now this part what we have it represented, it is the K3 and then with the manipulation of this part divided by this quantity here. So this is something like as a first order system here. So you can see K3 divided by 1 plus ST3 because you can see that it is P. This is D by dt basically. So we can write it as S in the Laplace transform. We have written it as S here, right? So it is this one. And now this at the moment again when you go back, this one K, so again del psi D is K3 times the this quantity minus K4 times del delta, right? So you look here, this is del EFD plus and then K4 del delta, it is here. So you can say because uh, K3 times del EFD. So at the moment, it could be a constant value or a zero value minus difference of this one. So we have this quantity here, right? And then how does we want to understand how the just see uh, the rotor angle delta which you had it here, it is actually the voltage angle, right? Or the MMF angle basically. And the MMF angle is that corresponds to the flux. That means how does the flux distribution takes place in the generator part. And in fact, it is the uh, angle, rotor angle, it is the angle suppression, the difference of uh, the main field MMF and the resultant field MMF, right? So thus, how does so when you talk about the flux, so that means how does the changes if there is a uh, variation if there is a variation in the field flux and how the variation in the field flux will affect the system stability, because we are talking about the rotor angle stability. So how this rotor angle stability, rotor angle variation is affected by varying the field flux. We want to understand this part here. So with that, what we have written here, dt by dc, that means angle here. So rate of change here. And we have written in this in this part here, right? And in fact, you can see here, this is del TE, del TE. So this is in fact K1, right? And then let's say this is uh, K, it will be K4, K3, K2 in the numerator, right? K1, K3, K2 in the numerator, and then in the denominator it is 1 plus ST3. So the quantity which you get it over here, right? It is this one here, right? And this is the minus sign. So you have this minus sign. So that's the del TE, what you get it here, it is actually K1, uh, K1 minus of this term here. And then because just see, K4 is also del delta. Here you have del delta and K1 is also del delta. So that we keep it here. So we are just taking the rate of change of torque with the del delta. So this is this term here, right? And then, so now we say that, yeah, this is what I refer. So what is, how does the torque with respect to the angle will change? And this is because of field excitation. So that means what is the effect of variation in the field flux? So it is this way. So this term we have it removed, and then we have this and return because just see, we are writing down in terms of S here, but this term is independent of S here. So remove it. So we have only this term left here. So we have this way. In fact, we want to solve it. Yeah. So we have multiplied by 1 minus ST3. Yeah. Yeah. Right. Now, if you have a, because S represents the frequency term here, right? So for a given oscillating frequency, S is equal to j omega here, right? In fact, S also has the real part because, but here we are ignoring it. That means we are ignoring the damping part here. So what is the change in the torque with respect to the field excitation? So we write in this way. So in fact, it is the same way here. So this is del delta. We are multiplying it over here. So it is this part, and then it is this part here, right? So we get this way. So that means there is some term that is a synchronizing term, and then change in the flux here, and then angle delta here. So in fact, this thing, what you also, this is the torque, electromagnetic torque. Now this electromagnetic torque, it is actually the phasor sum of two components here. One is the synchronizing torque, which will be a function of delta. Another is the damping torque, which will be a function of omega here. So thus on the plane, on this axis, we have omega. On this axis, we have delta. So now delta is related to synchronizing torque coefficient here. So this is the synchronizing torque coefficient or synchronizing torque, you can say, into delta. And then this is the damping torque, and then del TD multiplied by del omega. So it is this part represents the damping torque here, which is in phase with omega. So the electromagnetic torque here, it is basically the phasor sum of these two, synchronizing torque coefficient, also synchronizing torque factor, you can say, or the damping torque factor here, that way. Right? Anything on this part? Yes, please.
No, it's okay.
Okay.
Should we remember all these equations for the exam?
No, but only thing is that I just want to explain on what factors the system stability is affected, basically.
Okay.
How it
So the
changes.
basic concepts.
Yeah, this is the concept actually I'm trying to explain here. Equations we don't remember, in fact it's not required, but
Okay.
because when I going through the equations, because it is from these equations only we draw this block diagram, right?
Yeah.
So but in the exam it is not expected that okay you draw this block diagram, but you should know how how the quantities are related, basically. For
For the
example,
knowledge.
yeah, that the electromagnetic torque, it is related by K1 into del delta and K2 times del psi d. But and again on this side we have some more terms here including. So how the equation gets changes, that is important. Yeah, that is
Okay.
important. Yeah. So then if you have some oscillating frequency, so we have represent in this way, and then we solve it here. In fact, and it is this way. This is for del delta, and this is for del torque here. So it is this. So we get in this way. But I will give you one example, numerical example on solving this later on. Right, I have some examples. So you there you try to understand how we have this part solved, basically. Next part is the because you see we have considered initially we started with from here. We started with the classical model of a generator as a second order form. We had this one. Then next we had included the field circuit of the generator. We had this one, right? And next because we want to consider the complete excitation system and the control part basically, right? And thus now we have this one included because the previous block diagram, this one, how this is the field voltage, the field voltage to the field circuit, or that is the rotor of the generator. Here we have set. What does this mean? Can anybody say? When I say dial
What
EFD is 0, what does this mean?
means the field is not changing?
Not changing, it is constant. So that means
Yeah.
whatever the initial field voltage you have applied to the field circuit, it is same. So that means you have the circuit analysis without any deviation in the field voltage. That means the field circuit, the field voltage being kept constant, being kept constant. Yes, right. So next part, when you consider the exciter circuit, so how you will obtain the field voltage to the generator rotor? That will be from your another source, and that source is your exciter. So it is the exciter which will supply or which will provide a field voltage to the field circuit of generator to build up the voltage across the generator terminal. So here we have the exciter. In fact, I will discuss, there is another separate chapter, what are the different types of exciter and how we model them. So we will have it later on. But at the moment, the exciter is represented by this box, and the model of a the model of an exciter, it is as a transfer function representation here. Just consider a simple transfer function, right? Then since the exciter is required to regulate the generator terminal voltage as per the reference value. So here it has a input. What will be the reference voltage to for the generator terminal, right? And thus another one, here there is a feedback. So there is a feedback of the voltage from the generator terminal, basically. So you can see here that this is the generator terminal voltage here, right? And it is through the transducer, that means the measuring device, it is transformed to this state variable here. Because this is state variable, because here you find that the model or the transfer function of a measuring device, it is as a first order form. So it will be there will it is a state variable here, that means. And then you find that the terminal voltage of the generator, it is related to another constant K5 and K6 here. And K5 is times del delta and K6 times del psi d. So as a whole, in the SMIB system, remember, there are 6 constant, K1 and then K2. In fact, K3 we get it from here basically. I have not shown it, but we get it from here. We transform this S of T3 into another constant. And then in fact, here it is a complete transformation. We get it here. Basically, it is K3. Because in some book, you will find that this term has been included with the K3 something, right? That is also possible. And then you have this K3. And next, this one is your K4. Here is your K5, and this one is your K6. So the complete model of SMIB system, They are represented as case constant, K1 to K6 constant basically. And thus, the previous representation of the matrix here. This is what we had. With the field circuit inclusion, we had 3 state variable, right? And now when you consider this part, then what you have it here, one more state variable, this one. So one more state variable is added. And of course, this del psi FD will also be modified. All right. So that is now represented by this element in the matrix here, because we will take into account this representation. So it will be modified. And but here again, it is shown as a single input here, right? But you can always have it with the V reference as an input also. That is also possible, right? And that's in fact you can refer Kundur this section for this constant here, and then again the B is constant here. So the torque, the electromagnetic torque, what you get it here because of changes in the field excitation. And now we have the changes in the field excitation obtained by your exciter circuit, AVR and exciter circuit. It's this one. So we have this way. So what you find here, it is written down K2 times del psi D. And what is del psi D? Here it is this one. So you can see this term, it will be K3 divided by 1 plus S3. And then you have here the quantity K4 into del delta. So this is minus sign. So it is minus K4 del delta. Then plus. So it is del psi, in fact, this quantity. This quantity we have written down further as this term. So it is this way. And this quantity will be equal to this one divided by this term. So what you had it here is this one. And this quantity is multiplied here. So this quantity will be equal to K5 into del delta and K6 into del psi D. So it is this one. So maybe I could say it as this one, what you have it here as because of del ET, del ET, and then K3 is here. So we have K4 del delta, this one. So this one, you can say this quantity is your del EFT here. Del EFT, this one. And then we can have it. So now we do some manipulation here, and then we write it out in this way. So what you find it here? The changes in the rotor angle, it is now written down, right, in terms of the field flux variation here. And that field flux variation, it is now controlled by your excitation system here. So this is very important relationship basically that shows how does the angle, how does the rotor angle will change if you have some disturbance applied here. All right, if you have a part of, if you've applied the some changes here, right? So in fact, the AVR, what we have included, the effect of AVR on damping and synchronizing torque coefficient, they are basically influenced by what is the model of excitation system here, right? So how you have your exciter, all right? And then again, the K5 constant, it is this one. So thus the effect of AVR on the synchronizing torque and the damping torque coefficient, it is this one here. They are influenced by this. And if you have K5 less than 0, right? Because just here, this one, right? So if you have K5, what do you mean by K5 less than 0? It is negative basically, right? Then the AVR will have a positive synchronizing torque here. So in fact, I have some example here, understanding how the considering different AVR settings, how it affects the torque. Yeah. So I just say I have considered simple excitation system model. So let's say this is a gain here. All right. So because I will discuss later on a fast acting excitation system, let's say the rotating one, they can be simply as a gain representation. So here we have a gain representation. And then let's say K5 is negative. Let's have K1 value, K2 value, K3, K4, T3, K6, and K, but consider K5 as negative, right? And there is no load damping constant, 0, with this inertia. Now, from the previous relationship, what we had it here, right? This one. So we had it, the torque written down in this way. It is right. In fact, it is modified because this term is represented by Ka. Yeah, okay. It is represented by Ka. So we have it here. And we had this. And now we will analyze how the changing the value of gain. All right, we gain, let's say gain is 0, 10, 50, and so on. What is synchronizing torque coefficient? And what is, this is the complete, and in fact, this term and again this term. So this is the synchronizing torque coefficient with the field, dependent upon the field here. And this is the one with K1 plus Ks here. And this is only with the KD here. So how does they have changed here? So what you find? Can you guess here? For some values of gain here, for some values of the gain, the synchronizing torque coefficient, they are negative here, right? They come out to be negative. And then for some values of gain here, higher gain, if you have higher setting of gain, exciter gain, you find that the damping, the load damping coefficient, that is also negative here. All right, remember one thing, the torque which we had it here, this one, it is actually in this way, right? K1 minus this term, and we have written down the torque. It is K1 times del delta plus K2 times del psi d. And as such, the product of the damping torque coefficient into this, and the product of synchronizing torque coefficient into this, that is the factor, synchronizing torque factor and the damping torque factor here. And here we observe that for some values of the gain, so the synchronizing torque coefficients, or the fact that they are negative, and for higher values they are negative. But if you have the synchronizing with K1 plus this one, so all these values, they are positive here, right?
Okay, but what does this mean? I don't understand in terms of the system.
At the moment, what we have done, we are trying to analyze how does the torque because the torque is written down in this way now, right? Right, and the torque is related to angle delta here, right? And here we have changed the value of gain here, this one. So if the gain is 0 or 10, 15, 25, 50, and so on, right? Then the Ks, when you look at Ks term, it is uh, because when you look at this one, this is actually Ks here, right? This is Ks, and this is Kd term here, right? So Kd times del psi Fd, in fact, and then Ks is the del psi Fd here. It is this term. So how does, because the torque, this torque, the total torque, this one, that is basically the sum of the two. So it is possible that this term becomes negative and this is positive, or this term becomes positive and this term becomes negative, right? So it has to be balanced. The torque, the electromagnetic torque with the change in the field excitation should be for a case when both the quantity are positive, right? Now, if I take this here, if you refer to the table here, with the gain Ka 0, Ks is minus this quantity and Kd is this one. So what will be the net? Net will be 1.772 minus this quantity, right? Agreed? So the torque will be reduced.
Yeah.
Then. The torque will be reduced. So if you have these sets of the gain, then it has negative synchronizing torque component or coefficient basically. And if you have higher gain, then the damping torque becomes negative here. All right, the damping torque component becomes negative. But if you have Ks is equal to this quantity, then for all the range of the gain, we have this one. But that means you need to have this quantity to be more. All right, this quantity you want to be have more with the, because if I say K1, because here just see the K1 you have considered 1.591 here. This is 1.591 here. Am I right? And if you have something, let's say Ks is del psi Fd. So when you subtract it, how much you get it here? It is this value, right? So
Yeah.
this is what's Ks here. So, but if I say something, if let's say you assume that Ks had been something 0.5 or 0.6, okay, this is for much higher. But the synchronizing torque coefficient has to be positive basically, right? And that is with both K1 plus K psi, which you have it here. So in this case, both the quantities, they are positive here. All right. Now, if you take the total torque, right? Total torque in this case, it is 1.585 plus 1.772. Agreed? Then for this case, it is this quantity. For this case, it is this. But if you have gain this value, if you have gain of this value, then the total torque will be 1.5812 and the difference of this quantity, right? So that means for a higher gain setting, the torque, the electromagnetic torque reduces, the net torque reduces because the load damping factor becomes negative for a higher gain factor here. This is what it reflects here.
Okay, so when that happens, does that mean the machine will be unstable?
Yes,
or the
in that
system will be
case,
unstable?
that means it reduces basically. It reduces. So thus it is very important to maintain a balance between the synchronizing torque coefficient and the damping torque coefficient here. Right? It is important that to balance between the two quantity here.
But here you started with 0, the damping.
Yeah,
So, right?
yeah, it is. We started. Let's say there is no gain. What could happen?
Mhm.
Yeah, it started with that. Yeah, but
No, I'm
normally,
saying there up in the examples you said KD equal to 0, but this is a different KD or
here, yeah, it
yeah,
is
this
with the
one.
different one. It's different. Yeah, it is. But here you said it is 0. Oh, okay. This is this KD. What you talk about? It is a function of this one, del psi FD.
Okay,
It is a
and
function of
that
del
KD
psi.
is
Yeah,
it's,
that
it's a
this
different
KD is
KD.
yeah. This is different. In fact, this KD I'm talking about this one. This one.
Okay.
This is actually a factor. It is a factor.
Mhm.
It is a factor actually. Yeah. And and again, you can refer to the book, and we have calculated this value for a angular frequency of 10 radian per second. So in fact, this calculation is based on from this one. This calculation, what you have it is from here. Exactly. Right. Yeah, maybe I can. Yeah, I hear you. It could be a little bit more explanatory. Now, just see from the swing equation, we have this relationship, right? So this is the swing equation. That this one. In fact, it is the same form of the relationship because if you refer from the second order model, what we have it here, this one, because del delta and omega, they are related, right? We have them represented as a state equation form, I think here, yeah, this one, right? So now this is del delta. Now del delta is del omega. In fact, it is really how they are related, right? So you substitute this over here, okay? So thus, in that case, it becomes a d square delta by dt square here. And then we have this term. So this is mechanical torque, electromagnetic torque, and the load damping constant part here. So we just manipulate it here this way. And now you see the torque. It is the synchronizing torque and the damping torque. And the synchronizing torque is the synchronizing torque coefficient times del delta, and the damping torque is damping torque coefficient times del omega, right? And this is the case we have show it with a constant field voltage. That means this one, here, this one. That means the field voltage is not regulated. It is maintained constant, right? Then what is the situation? That means there is no AVR here. So when you don't have AVR, then let's say, because this is del omega, this is del delta, and this is del torque here. So damping torque coefficient and the synchronizing torque coefficient, it is this one. Now let's say if you have positive TS and positive TD, right? Positive TS and positive TD, because refer from the table, right? Positive T, this is all negative. This is all positive, and then this is all positive, but this is all negative here, right? So in that case, if both are positive, then what will be the change in the delta? It will go. So you find it that rotor angle will settle down after some time. So this is a stable response if you have both TS and TD positive, right? But if TS is negative, but TD is positive, then you will get a non-oscillatory instability. So you will have non-oscillatory instability. So if you get this form of the deviation in the angle, it means that TS is negative here. So this is non-oscillatory instability, right? And if you consider excitation control, so that means with AVR included. And then again, it can be a case both positive TS and TD, then you get a stable response. And if in case you have positive TS, but TD is negative, TD is negative, then you will have an oscillatory instability. That means increasing amplitude of oscillation here. right? So positive TS, negative TS, negative TD give you oscillatory instability here. So that's the constant with the constant field voltage. KD is greater than 0, right? This part you must know. That means TD will be positive. KD will be greater than 0. And in fact, KS will be equal to what is the KS of the network plus KS of, because if you remember earlier when we discuss this, we talk about the synchronizing torque coefficient with this one. We talk about the synchronizing torque coefficient here with only with the network. So we are considering because here which we had the KS defined. It is taking into account what is the reactance of the line. So it is of the network here. But when you consider all other components, then you have total chaos, net chaos will be what is the chaos of the network plus chaos change because of field excitation. And it can be perhaps can be less than 0. So that's why it is says negative torque here, negative synchronizing torque coefficient. But if you have with AVR included, then KS is greater than 0. So that's why you see TS is positive here. TS is positive, but KD, KD will be what is the, if you remember earlier we said the load damping constant of the generator and the network and including the load here. And then what is the change in the load damping constant because of change in the field excitation. That can be less than 0. So thus it can be negative here. And so with the two different cases, the system can be stable or unstable here. But normally, we always have excitation control implemented in the generator part. So if you have that, then synchronizing torque will be greater than 0, but damping torque can be less than 0 as well. That is possible, right? So we stop here and then we continue. If you have any query, yes, please. Yes, Ibrahim.
No, I'm
Max.
good.
Okay. Okay.